I'm trying to exit from the presentation, but I cannot. I don't see much. Sorry, I'm in trouble with the.
It's Natasha here. Can you keep your presentation? Can you move to slide 32, please?
32. Okay.
32.
Sorry, I'll do in a moment. 32.
Yes. On the right figure, part C, if you like blur it by squinting at it, you can see some hexagonal pattern emerging. Do you have any explanation?
I'm not understanding. Sorry, Natasha, I'm not understanding.
I'm talking about part C of your figure.
Yes, yes.
And if I squint at it, below my vision, I can see a hexagonal pattern emerging. And I'm just wondering whether you have any explanation for it. Because your lattice, as I understand, it's either rectangular or square lattice. And having this kind of unusual hexagonal pattern, well, it is unusual. Do you have any explanation for it?
Yeah, I mean, bifurcation is usually loss of symmetry, and usually the system moves to a lower level of symmetry. And actually this occurs not only in the numerical simulations that we have performed, but also in the experiments. If we look for a moment the experiments that we did here, we see that these patterns are very regular, beautiful. And so I think this is related to the fact that the system goes from one level of symmetry to a lower level of symmetry, but doesn't lose completely all the symmetry. This is the case when we have shear bands, but it's not the case when we have a micro bifurcation. But if you ask me for a deeper understanding of this phenomenon, I don't have it. I mean,
fair enough. Thank you.
Thank you, Natasha.
Are there any more questions? So I've got a question on the cloaking side. Regarding your plate, for the last experiments, do you plan to make any further experiments with this kind of cluster of randomized cluster of poles?
Well, you mean if I'm trying to, I'm going there. I'm trying to do the experiments corresponding to the simulation. You mean?
Yes.
You mean this experiment? Let me do this. You mean this experiment? Well,
yes,
I would like, but the problem, yeah, I would like. The problem is that an experiment like this easily takes 6 months of hard work. So I would like, but by the way, I have to mention that unfortunately our lab has been closed in the last 5 months since the beginning of the epidemic, and is still closed in the sense that we can go there, but the only people admitted are me and Diego Miseroni, and so we are two. Of course, I could help him, and we could help together to experiment. But usually in my lab there are many people working, and so. But it would be interesting to do this experiment, sure. Although I'm confident that it should work. But these experiments are usually less easy than they may appear, because, for instance, a big problem is to prepare the correct stiffening frame for the rod. That's very difficult. And then another problem is to attach it correctly to the plate, that one needs a very strong glue which has to be used. And so if I would ask to a PhD student, he would not be able to do that. And so I have to ask directly Diego, who is able, But of course, he has many things to do. He has to write papers, to write equations.
I've got another question. So essentially, you have a cluster of cloaks here, and there is no interaction between the cloaks?
No, because they are reinforced. There is interaction in the case that they are the case on the right. In this case, there is interaction in the case on the right. But in the center, since they are properly cloaked, they are invisible. So our goal here was to try for the first time to show an example where there is not only one cloaked inclusion, but there are many and random. Because if one is invisible, well, it should be invisible even multiplied by 7.
May I ask a question? Can you hear me?
Do we hear you? Yes.
So here in this cloaking experiment, you tried flexural waves. Could you make the same study, or can you reinforce your plates to survive in-plane shear waves?
Well, to tell you the truth, this is not only flexural wave, it's also torsional waves. There is both flexure and torsion. Anyway, if the question is if I can do something similar to this in plane, the answer is yes, we can try. We wanted to do this. Actually, I asked one PhD student to do this, to work, to produce this reinforcement for in-plane waves. But the problem is that this guy now is home because of the virus, and so this thing is standing. But I'm confident that this can be done also for in-plane waves. By the way, the experimental verification of in-plane wave is very complicated, more than flexural waves, because for flexural wave we have used stroboscopic light and fast recording. But for in-plane wave, you should use other things, for instance, laser scanner or something like that. So it's more complicated, but I think it should work.
Okay, thank you.
You're welcome.
I've got another naive question. Your scheme so far for pre-stressed materials, it's two-dimensional, isn't it?
Yes, it is two-dimensional.
So I guess that the similar route would work in 3D. So we could also, yeah.
Exactly. I mean, the scheme is exactly the same. And the ideas are exactly the same. The only problem is that it becomes more complicated to handle. But of course, the scheme doesn't change. The mathematics, the tools, everything remains the same.
Wait, but in 3D, you don't have some kind of conformal mapping. I think you use some kind of conformal mapping of your grid. No? No? Okay. So it would apply just the same. Just incremental.
Yeah, just the same. Yes, more complicated, but the same. I mean, the scheme doesn't change at all.
Okay. And it's really reminiscent of the theory of nonlinear cloaking of William Parnell and Andrew Norris. No, somehow. Are there any similarities?
No, we are not in a position to test something at that level of complexity. Because if we would try to do an experiment, that would be too complicated, at least to me. So I'm not able to judge about that.
Because as soon as you have some pre-stress, usually it's non-linear.
Well, it depends. The way I'm using the pre-stress is in a linear way, because everything works like this. The material is pre-stretched or pre-stressed in a way that it remains homogeneous. And so the differential equation have constant coefficients. And then the perturbation which is applied, it's completely general. And so this perturbation changes everything, but it's only an increment. And so it's the linearized response of a nonlinear curve. So it's the tangent to this nonlinear curve.
But in your theory, you don't have any higher order gradients coming into the theory because of this pre-stress?
Not higher order gradients, no, because our theory is standard. Homogenization theory by Nick Triantafilidis, Pedro Ponte Castaneda. We did not invent this theory, but this is how to say planned for standard elastic materials. So we don't have, let's say, strange effect. Of course, the stress tensor is not symmetric, but this is not because of Coser effect. This is because the first Piola-Kirchhoff stress tensor is unsymmetric. So it's not the same thing. So this is standard elasticity. I mean, if we, let me find the image, the proper image. The computer is very slow. Yeah, if we consider these constraint equations are standard for linearized nonlinear elasticity. So we deform a nonlinear elastic material, and then the linearized response is done near a perturbation. So we have this guy which has been before deformed nonlinearly, and then is incrementally perturbed. So these constraint equations relating the increment of first Piola-Kirchhoff stress tensor to the increment of the gradient of incremental displacement, this relation here, it's standard, can be found in books of nonlinear elasticity. It's linear, still linear.
Really, you don't think you can map your theory on some kind of micropolar elasticity theory or some kind of scheme of, I mean, it stands on its own, it's something else, totally different.
For the moment, this behavior is out of the story for this moment. But of course, we have done this also thinking one day we should be able to do that. To do that, we have to think which is the correct matching. I mean, there is a matching here between the continuum and the lattice. Continuum and lattice. If we would like to introduce higher order effects, then we have to think which kind of matching to introduce, which to me is not something easy, but there are things done in this direction by many people, including John Willis and others. But to me, up to this level, I know exactly how to do. To a higher level, I don't know, I'm not confident. Mm-hmm. But we would like to go in that direction.
Mm-hmm. It's quite fascinating. So, are there any more questions on any other parts of Davide's talk?
Can I ask a question, Sebastian?
Yeah, sure. Please go ahead.
Thank you, Professor Bigoni, for this beautiful presentation. It's a little bit hard to follow because of the equations. But I have very naive questions, 3 questions exactly. So can you go back, please, to the slides in which you show the negative refraction effect?
Yes. Yes.
Yes. Did you calculate the diagrams corresponding to the effect?
I didn't understand. Did I what?
Did you calculate the band diagrams to demonstrate this effect? Are you expecting to identify bands with negative slopes to explain the negative refraction effect by considering the pre-stressed unit cell?
I mean, actually, what we did is this numerical simulation, and I didn't capture the question because the audio is very low here, so I didn't understand exactly. But what we did was to do this simulation and to check where the wave was going, and it's so clearly localized that the roots outside this layer do not move, and so it's pretty evident.
Yes, but by my question, I want to know if you take, for example, a unit cell, okay, for the stressed part, and you calculate the band diagrams, And for these frequencies, specific frequencies, you can see if there is a negative slope in this area.
Yeah. Now I understand. Yes. I think we have done this. I don't have an immediate answer now, but I should take the paper and look. I think we have done it. Yes, for the unit itself, sure.
Okay. So my second question: if you take this, you are depicting here the changing of direction of waves. So this because of you are taking into account the fact that we are the wavelengths are a bit small compared to the area, the negative refraction. That's it?
The wavelength is small compared to the area of negative refraction.
It's linked to super resolution, I think.
Yes, it is. Yes, it is small.
It is small. Okay. So now, if can pre-stressed area be resilient to long waves? I mean, to consider it as a meta surface this way, to change to any direction. Do you understand my question?
Not much, because your voice is going forth and back. For me, it's very difficult to follow.
Okay, if the wavelength now is huge compared to the this width of this width of the pre-stressed region, can we fabricate meta surfaces with this theory?
I have no answer. I understand the question, but I have no answer. I have to try. I would need to try.
Okay. And my last question, in the cloaking experiments, can we calculate again the dispersion curves in order to match the tuned case with the original one? Because you are demonstrating the effect only for discrete states, not for the intermediate states between the eigenvalues.
Yeah. I see what you mean. Yeah, I think we have done this numerically, and we have obtained what you say. But here the message is different. I mean, engineer thinks that if two systems have the same frequency resonances up to a while, then these two systems will become dynamically almost identical. So the message is that if we take these three structures, the first two, 1 and 2, have the same eigenmodes up to the 7th or 15th eigenmode, and so we are prone to believe that they behave the same thing as the same thing, because these are the free vibrations, the resonant mode, and so they have first coincided in the first, in the second, in the third, in the fourth, and so on, continuing. We have stopped the experiment because at a certain point we see nothing. But if we do this numerically, we continue to notice this coincidence, and so it means that the two systems have the same spectrum. In any case, we have done numerics looking for dispersion surface and these things, and they worked, I mean. But then we wanted also to do an experiment to show this. For us, the experiment is very important to us. And so we started.
But I guess we can at least do it numerically to have an incoming wave, taking this tuned inclusions, and to see if we have scattering in the case of intermediate states, not only for discrete states.
Yeah, this graph of scattering is like that. There are all the frequencies here. And this is a measure of scattering. 0 means that scattering is completely excluded. 1 means that the cloaking doesn't work. And all these spots here are all cases that we have done numerically. And so the behavior is very, again, actually we did this well before than the experiment, because since one experiment takes 6 months, before to do the experiment, we have to be convinced that the experiment will work. Otherwise, it's wasting a lot of time. And of course, numerics is much quicker than experiments. And so first we have numerically experimental, what you say, with a broad range of frequencies. And it works always very well. Sometimes better, sometimes worse, but...
Yeah, sounds clear, Professor. Thank you.
Thank you.
So do we have any more questions for Professor Davide Bigoni? Okay, so I would like to thank you again, Davide, for this really inspirational talk. It's a really wonderful talk, actually, on many aspects of mechanical metamaterials. And I would like to remind everyone that you can still contact Davide via email. I'm sure he'll be glad to answer your many possible questions. And next week, actually, is the 14th of July, so which is French bank holiday. So we'll skip this week. And in 2 weeks' time, it will be our very own Professor Richard Craster from Imperial College London who will deliver the seminar on elastic metamaterials. So thank you very much again, Davide, and thank you everyone for attending.
Thank you, Sebastian. Thank you for having given me this opportunity to speak to many people. Thank you for this kind invitation, and I hope to meet you soon. One day without virus, hopefully. Thank you to all. Have a nice afternoon.
Okay, and let's this awful virus. Okay, bye.
Bye-bye.
Bye-bye.